All right, so for today, for 8.2, we're looking at inverse relations and functions. So our objectives, we're going to find the inverse of a relation, determine its domain and range, state whether it's a function. We're going to determine whether a function is one-to-one, and we're going to use some function composition to determine whether two functions are inverse functions. So there's a lot of new vocabulary today. First up, inverses undo each other. So we have inverse operations that we talk about all the time. Addition and subtraction are inverses because they undo each other. Multiplication and division are inverses. Okay, so we're going to take this idea of inverse, something that undoes itself, and apply that to functions today. Right, taking a step forward and a step backwards are inverse. Taking a step right and a step left would be inverse, right? Like a step W.
It's 7.
I like it. Okay, so an inverse relation. If a relation, which we're calling R, contains the ordered pair AB, its inverse relation, which we write as R to the negative 1, we still read it just as like inverse of R, okay, contains the ordered pair BA. What happened? That's it. Inverses swap. Instead of being Abba, it's Ba. Okay. So the domain and the range, that's the other thing, the domain and the range of the relation are switched to obtain the inverses domain and range. Okay, so we switch the x and the y, we switch their domain and range, like everything is just switched over. Okay, so the notation used to indicate a relation's inverse, that r to the negative 1, is read as the inverse of r, or r inverse. Okay, inverse function. Don't confuse this with a negative exponent. All right, then if you look at the graphs over here, okay, all they have done is this one is r, and this is its inverse of r. So you should notice we had 3, 1. Now we have 1, 3 as the first coordinate. So they are just switching. But that means if we did a mapping diagram, that these switch places, like the domain becomes the range, and the range becomes the domain. So question so far. We get that inverses just switch places. Okay. I like it. Where does it get bad? Okay, so maybe not just yet. All right, so example 1 says relation Q equals 2, 1, 4, 1, 6, 2, 5, 4. Describes the vertices of a quadrilateral. Find the inverse of Q. Then graph both Q and its inverse and describe the relationship between their graphs. All right, so the first thing we need to do is switch the coordinates in each ordered pair. Okay, so we're going to do the inverse of Q. All right, so what's my first coordinate, Ethan?
1, 2.
1, 2. What's my second coordinate, Brandon? 1, 4. What's my third coordinate, Josh? 2, 6. And what's my fourth coordinate, Mrs. Talbert, is 4, 5. I like it. Okay, so step 1, we did it. We switched them. Ta-da! We have an inverse. Now we need to graph the ordered pairs. Okay, we want to graph both of them so we can see both of them. Okay, so we have 1, 2, 1, 4, 2, 6, and 4, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, it told us it was a quadrilateral, so I'm going to go ahead and connect these so we can see that it's a trapezoid. Now, if you have a pencil, if you want to do a different color, or I have a pen you could borrow, you could, for the dash, you do not have to, we're going to use a dash mark for something else. I'm going to use a different color. So I'm going to put my Q, relation Q in red. So I'm going to go 2, 1, 4, 1, 6, 2, 5, 6, 1, 2, and 5, 4, 1. Okay. So we've graphed the ordered pairs. You did do something wrong. Those look wonky. This one looks wrong. Okay, I was like...
I put 4 7s.
You did 4 7? Where's your... I know you don't do a lot of notes. Okay. So what do you notice about the Q and the inverse of Q? They are mirrored. Do you know where they are mirrored?
They look like wings.
They do kind of look like wings?
From the middle to 0, 0.
Okay, so it's like the diagonal?
Yeah.
Okay. So that is true. It's mirrored on this diagonal here, which is called the y equals x line. And that's what it says there. The graph of the inverse is the reflection of the relations graph in the y equals x. So it is, like you said, they're mirror images because it's a reflection there. Now, the cool thing about this, the little note after that says, when a relation or function is expressed as an equation in x and y, it doesn't say that. A rule for its inverse can be found by switching the variables in the rule and then solving for y. So never mind, it doesn't tell you anything there. I lied to you. But oftentimes, that's what's going to happen is you get a reflection across this y equals x line. So we'll talk about that a little bit more later.
What if it's all about y equals x?
Then it will reflect the other way. Like, one point will stay on it. If it crosses it, then it reflects and stuff too as well. Okay. So far, so good. Okay. So we're going to apply the same principle with the next thing. So when a function, when a relation or function is expressed as an equation, so we're looking at it as an equation with x and y, a rule, so we're looking for a rule for its inverse, can be found by switching, we're still switching, the variables in the rule. So we switch the variables and then solve for y. Okay, so here's the deal where we got to remember, what is f of x? It's the same thing as y. Okay, so y equals 2x plus 4. So this says I need to do what with my variables to find the inverse? I need to swap them. So x is going to equal 2y plus 4.
You don't bring the 2 with it?
Say what?
The 2 on the x. You don't bring it with it?
Nope, you just switch the x and the y. That's a good call. Okay. So then if we solve this, we have minus 4, right? And so x minus 4 equals 2y. We would divide by 2. So we would have x minus 4 divided by 2 equals y. Actually, I could, let's simplify this. Okay, there we go. That'd be great. 1/2 x minus 2 equals y. I was like, I should simplify this, right? Because x divided by 2 is 1/2 x, and then negative 4 divided by 2 leaves us with negative 2. Okay? So, how would I find the rule? One more thing here. How would I write this as a function rule? That just means I need to use function notation. So f to the negative 1. You got it? Of x. Because we call that the inverse of x equals 1/2 x minus 2. You got it. Good. So I'm not killing you so far? Okay. So again, g of x, what's that the same as? Y, right? Like we just take it out of function notation. Then what do I do? I switch the x and the y. Okay, so x equals y squared minus 2. Now we plus 2. Square root it. Can't find the square root of it. So we are going to put a plus or minus in front of it, right? Because it could be a positive or a negative. We don't know. So we'll say plus or minus. And then function notation is the inverse of g, not f, my bad. Okay. So the inverse of g of x equals plus or minus the square root of x plus 2. Perfect. Did you just have a sour face? Like, what was that reaction?
I flipped the page and didn't like it.
You flipped the page and didn't like it. Okay. All right, so we flipped the page. We're going to look at a picture here first. All right, because now we're going to talk about the graph kind of functions. All right, so it's hard to tell up here. So I'm going to make my g of x red so we can talk about it a little better. And I'm going to make my inverse of g of x the blue.
It's not really opposite though.
That's right, the red pill and the blue pill. You got it. What do you mean it's not really opposite?
Because if one is up, should the other be down?
But it doesn't, I never said that they would be opposite. They undo each other.
Yeah. So undoing would be opposite. Basically. If you have positives, the opposite of is a negative, they undo each other.
Do they though?
Yeah.
Positive and negative undo each other, but in this case, right, because remember, we're taking and we're changing, just like the example that we did, we switch the x and the y, and it reflects around what axis? The y equals x axis. Okay, so this is the y equals x, not axis, but line. Okay, but it reflects around that line. So that's the thing. If it depends on what we're talking about, like how it's undoing. If we were talking about stepping forwards and backwards, okay, forwards and backwards undo each other, but they reflect across what axis? The line that I'm stepping across. Okay, so if I was looking at this axis and I was here and I step forward, well, maybe I shouldn't. Let's put my line on my dot on the axis actually. Okay, so if I was on this axis and I step forward, then yes, I would step backwards. Okay, if I was on the right, or if I was here and I stepped right and then stepped left, that's a reflection as well, but it's across this line, not this line here. Does that make sense?
Yeah, but I still don't see why they both would be going this way. So I feel like if you're going across this line, they'd be facing opposite ways like this. Instead of
So that is the tricky part with these. That's and I'll have to think about, like, I don't have a.
And I suppose just when we write out the points, that's how it's gonna work out.
Yeah, like because when you switch the x and the y, they always reflect across that y. They should always reflect across that y equals x axis. Because we're dealing with the y and the x. Like, yeah. So let's look at these. G of x has a domain that's spelled incorrectly on your paper. I was just checking. I was like, man, it's a domain. Okay, so the domain is all real numbers. What do you remember that domain is? It's your x values, right? So these are the x values. Okay, and so the range is the y values. Okay, so all of the x values, because we're continuing to go up, and as we go up, it's also going out very, very slowly, but we can put in any x. The range, however, is limited. Y, it's y such that y is greater than or equal to -2. Okay, so it only goes this low. We're not going to have anything for y equals -20. How do we know that this is a function?
Because for each value of x, it
Only hits the line once, right? We do that vertical line test. Dun, 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 dun. Okay, passes a vertical line test, it's a function. Great. I'm going to erase my vertical line test. However, okay, so let's look at the blue version. So the inverse. What do you notice about the domain and the range of the inverse?
The domain of the inverse is
Not the range itself. They like switch there.
Okay, so they switched. The range became the domain or the domain. Because here our x values, and that should say x. My gosh.
They said it was Y's. I thought it was.
No, it should say x. There's all kinds of typos apparently today that I didn't catch. Must have been really tired when I was typing. So the x values we're only going to go to -2. We don't have anything for x when it's -7. Okay, only -2 and up. And then, like you said, the domain and the range switch places here. So why is this one not a function?
because it doesn't pass the vertical.
Doesn't pass the vertical line test, right? Like we draw a vertical line, it hits it 2 times, so it fails. It's not a function. Okay. So, we also have this thing called the horizontal line test. Okay. And so what that says is, so I'm going to erase all this, and I'm just going to focus on our original relation. Okay, so this one right here. Horizontal line test is if a horizontal line can be drawn through more than one point of a function's graph, then its inverse is not a function. So if I draw a horizontal line and it passes through it twice, we know that the inverse is not going to be a function. That make sense? It's like doing the vertical line test early. You're like, okay, because if I had this line like this, okay, or this coordinate graph, and I drew this line. We put arrows on it so you know that it's the line. And I did a vertical line test. Hey, it passes. Then I do a horizontal line test. It passes. Like that's it. That's the horizontal line test. Okay? Because here's the deal. We have the special description of inverses when they pass both. And it's called a one-to-one function. Okay, so it's any function whose inverse is also a function. So is this a one-to-one function? No, this is not a one-to-one. Okay, they're not one-to-one functions. Okay, so that was fantastic. I'm going to move up my diagram a little bit so we can see all the little pictures to help us, or move up my notes so we can talk about inverse functions. All right, so inverse functions are when a relation and its inverse are both functions. Okay, when a relation and its inverse are both functions. So if we look at the inverse functions, again, undo each other. So we've got this function machine over here. We could see if I put 10 in this machine, I get 24 out. I put 24 in the next machine, I get 10 back out of it. They undid each other. Or if I go the other way, if I put 10 in this one, I'm going to get a 3 out in the middle to put into this one, and I get a 10 back out. Doesn't matter what order. That's what this function notation is telling us. So the inverse function of f of x, or the inverse function of f of x, or f of the inverse of f of x is still going to equal x.
It's weird.
It is weird. But it also gives us, we have this diagram that I just showed you of f of x and the inverse of x. They pass the vertical line test, it passes the horizontal line test, whatever. They're both functions, so they are inverse functions. Because originally, like at the top, that one, right, was a function and not a function. So they're inverses, but they're not inverse functions. Okay. So.
That's where both functions are one-to-one function. So, well, is there a difference between inverse functions and a one-to-one function?
No. There's just two different names to describe them. Yeah, not a difference. Like we can describe you as a boy or a male, or same thing. Inverse you're going to hear more often.
I was gonna say, is that the third one?
Inverse is what you're going to hear more often. Okay, so then there's also this note I want you to, like, hopefully to help you understand, is that f of x and the inverse of f of x are both functions because they pass the vertical line test. Because they are both functions, they are inverse functions. Okay, so it's taking another step to describe them. So now in example 3, we want to show that g of x equals 4x and h of x equals x plus 1 divided by 4 are inverse functions. So how might we show that? What do you think? Solving what? We don't have to make a graph. Which problem? We want to prove that they're inverse functions, right? So up here, well, remember here, like they said, the inverse of f and f of x, or the f of the inverse of f of x. See how they did both of those? That's what we need to do. We need to say, oh, well, g of h, we need to solve g of h of x and h of g of x to prove that they're inverses, because we should get the same thing, right? Yeah, we should get the same thing. We should get x for both. So let's set that up. So we got g of x equals 4x, g of h of x equals 4 times x plus 1 divided by 4.
So then just distribute just every part of it? Okay. So then how does that work?
You can distribute it, so you'd have 4x plus 4. Nope, not divided by 16. Nope, divided by 4. Because remember, this is a fraction. It's 4 over 1.
You could just cancel it out.
You could have just canceled it out as well. And it equals x plus 1. Hold on, timeout. Yeah, I have another typo in my paper.
What's that?
It should be that g of x equals 4x minus 1. Because I was like, this
That's
is...
what I was looking at. I was
Yeah.
trying to think of where we would get the plus 1.
Yeah, I was like, this doesn't...
Stuff.
We had a mistake there. Yep. So we go back and add this, and it was like, only then would they actually be inverses of each other. But if we canceled, then yes, we would have had x plus 1 minus 1, which equals x. It's a big mistake to make right there. Jeez. All right, are we ready for h of g of x? Hold on, okay. Okay. I gotta note all my mistakes here. There's probably another one I've missed. Okay, so then with the next one, right, we're gonna do h of x is x plus 1 divided by 4. So then h of g of x, okay, we're going to insert x, that 4x minus 1, plus 1 divided by 4.
It's 4x.
4x divided by 4, which just equals x. Hey, you just proved that they're inverses. Because you did g of h and h of g, and you got the same thing. Now the bottom one, example 4, looks really hard, right? All right. says, given that the relations and their inverses are functions, given that they're functions, find the following. We don't need one.
You know, every time we go to something else and we don't have any questions, we say we don't need one, I end up not being able to do it. Like, every time. I can't.
This is not going to be one of those times. Because you just did this, right? You did g of h of x, and what'd you get out? X. Okay. You did h of g of x, and what'd you get out? Because they're inverse functions, right? So if you do the inverse of f and f of 3, what are you going to get out? So if you do g of the inverse of g of 1,492, what are you going to get out?
7.
Come on. I know you can do this. That number, 1,492.
Seems dumb, why would we even-
Why make that a problem if all it is rewriting it?
Because how complicated did it look to start with? Very. And how complicated is it actually? Very not. Correct. Because you just have to think, okay, if they're inverses, you have to recognize if they're inverses, you're just going to get that same number out. Because they undo each other. You do one and you do the other and they undo each other and you just end up with the same number you started with. Like, again, if I was on a coordinate plane and I started on 4, like 0, 4, and I took 4 steps forward, 3 steps forward and 3 steps back, I ended up in the exact same spot I started in. Okay? That's it. So you can get started on your homework.